Welcome to this fascinating exploration of the chocolate tempering paradox. Today we're going to understand why chocolate melts near body temperature but remains perfectly firm at room temperature only after careful heating and cooling cycles. Let's start with the central mystery. Chocolate melts around 34 degrees Celsius, which is just below our body temperature of 37 degrees. Yet at room temperature, around 20 to 25 degrees Celsius, properly tempered chocolate is firm and snaps cleanly. But if you simply melt and cool chocolate without proper tempering, it becomes soft, crumbly, and develops an unappealing white coating called bloom. So here's the question. Why does the cooling process matter so much? If chocolate solidifies below its melting point, shouldn't any cooling work? The answer lies in a phenomenon called polymorphism. Cocoa butter, the main fat in chocolate, can crystallize into 6 different forms, each with different melting points and structures. Let's examine the 6 crystal forms of cocoa butter. These are labeled as Form 1 through Form 6, or using Roman numerals. Form 1 melts at 17 degrees Celsius, Form 2 at 23 degrees, Form 3 at 26 degrees, Form 4 at 28 degrees. Form 5 melts at 34 degrees and is the desired stable form. Form 6 melts at 36 degrees, but is rare and hard to achieve. Only Form 5, also called beta crystals, produces the glossy, hard, stable chocolate we want. The other forms are either too soft or unstable. Now let's understand the thermodynamic challenge. Why doesn't Form 5 just appear automatically when chocolate cools? The answer is nucleation energy barriers. Form 5 is the most thermodynamically stable, but it requires the highest activation energy to form. The Gibbs free energy equation is delta G equals delta H minus T delta S. Delta G is the free energy change, delta H is enthalpy, T is temperature, and delta S is entropy. The lower numbered forms nucleate more quickly because they require less energy to organize, but they are thermodynamically less stable. Form 1 and 2 form readily but melt at room temperature. So how do we force chocolate into Form 5? This is where the tempering protocol comes in. There are 3 critical temperature stages. Stage 1. Heat chocolate to 45 to 50 degrees Celsius. This completely melts all existing crystals, erasing the thermal history. Stage 2. Cool to 27 to 28 degrees Celsius. This creates seed crystals of forms 4 and 5. Stage 3. Gently reheat to 31 to 32 degrees Celsius. This melts forms 1 through 4, leaving only form 5 seeds. You might ask, why does this specific 3-step process work? Stage 1 resets the system completely. Any pre-existing crystals are destroyed, giving us a clean slate. This is critical because crystal memory can persist. Stage 2 operates in a narrow temperature window where Form 5 nucleation is favorable. At 27 to 28 degrees, the supersaturation is high enough to form stable seeds. Stage 3 uses selective melting. Since forms 1 through 4 melt below 31 degrees, reheating to 31 to 32 degrees eliminates them while preserving Form 5 seeds. These seeds then propagate throughout the chocolate as it cools. Let's examine the mathematics of crystal growth. The rate of crystal growth depends on both thermodynamic driving force and kinetic factors. The crystal growth velocities versus equals K times delta T to the power n. Here K is a kinetic constant, delta T is the degree of supercooling, and n is typically between 1 and 2. Supercooling, delta T, is the difference between the melting point and the actual temperature. Greater supercooling drives faster crystallization, but favors the wrong forms. Delta T equals T sub m minus T, where T sub m is the melting temperature of the crystal form, and T is the actual temperature. At 28 degrees Celsius, Form 5 has a supercooling of 34 minus 28 equals 6 degrees. This is enough to nucleate, but slow enough to form the correct structure. Let's work through a numerical example. Suppose you have 500 grams of chocolate at 45 degrees Celsius. We need to cool this from 45 degrees to 28 degrees Celsius for stage 2. How much heat must be removed? The heat equation is Q equals mc delta T. Q is heat, m is mass, C is specific heat capacity, and delta T is temperature change. The specific heat capacity of chocolate is approximately 1.7 joules per gram per degree Celsius. This varies slightly with composition, but is a good estimate. Q equals 500 times 1.7 times the quantity 45 minus 28. That's 500 times 1.7 times 17, which equals 450 joules, or about 14.5 kilojoules. Critically, this cooling must occur slowly and uniformly. If you cool too quickly, you'll get a mixture of crystal forms. Temperature gradients create different forms in different regions. There's another energy term we must consider: the latent heat of crystallization. When cocoa butter crystallizes, it releases energy. The crystallization heat is Q sub crist equals M sub that times L sub F, where L sub F is the latent heat of fusion. For cocoa butter, the latent heat is approximately 120 joules per gram. This is the energy released when liquid fat becomes solid crystal. Chocolate is typically 30 to 35% cocoa butter by mass. So in our 500-gram example, we have about 150 to 175 grams of cocoa butter. Taking the middle value of 160 grams, Q sub crist equals 160 times 120, which is 19,200 joules. This 19.2 kilojoules is released as the chocolate solidifies. It must be removed by the cooling system or the chocolate will reheat itself, disrupting the tempering process. Let's dive deeper into the kinetics of crystal nucleation. Why does form 5 nucleate at 27 to 28 degrees, but not at 30 degrees? The nucleation rate, J, is given by J equals A times the exponential of negative delta G star divided by KT. Here, delta G star is the critical nucleation energy, K is Boltzmann's constant, and T is absolute temperature. The critical nucleus must overcome surface energy. Small clusters have high surface-to-volume ratios, making them unstable. Only above a critical size do crystals grow spontaneously. The critical free energy is delta G star equals 16 pi gamma cubed divided by 3 times delta G sub versus squared. Gamma is the surface energy, and delta G sub V is the volumetric free energy difference. Lower temperatures increase the driving force, delta G sub V, which reduces the nucleation barrier. But if we go too low, we get rapid nucleation of multiple forms. At 27 to 28 degrees Celsius, the nucleation barrier for form 5 is low enough that seeds form, but high enough that nucleation is controlled. This narrow window is why precise temperature control is essential. Now let's address why room temperature stability is so important. What makes form 5 special at 20 to 25 degrees Celsius? At room temperature of 20 to 25 degrees, form 5 is well below its 34-degree melting point, giving a safety margin of about 10 degrees. But forms 1 through 3 are at or above their melting points, so they remain soft or partially melted. This 10-degree safety window between room temperature and the melting point ensures chocolate doesn't soften in normal storage. It also explains why chocolate melts pleasantly in your mouth at 37 degrees. Improperly tempered chocolate crystallizes into forms 1 to 3. These forms are soft at room temperature, giving that unpleasant, waxy, crumbly texture. Let's discuss the bloom phenomenon. When chocolate isn't properly tempered, you often see a white, powdery coating develop. What causes this? Fat bloom occurs when unstable crystal forms slowly transform into Form 6. Form 6 has a different density and crystal structure, causing fat to migrate to the surface. Form 5 has a density of about 1.01 grams per cc, while Form 6 is about 0.99 grams per cc. This 2% difference causes volume expansion and surface irregularities. The transformation from Form 5 to Form 6 releases energy, but it's kinetically slow. It can take weeks or months at room temperature. Temperature fluctuations dramatically accelerate bloom. If chocolate is stored near its melting point, say at 30 degrees, partial melting and recrystallization occur repeatedly, rapidly forming Form 6. Let me give you a helpful analogy. The chocolate tempering paradox is similar to the diamond versus graphite problem in carbon. Diamond and graphite are both pure carbon, just like forms 1 through 6 are all cocoa butter. Graphite is thermodynamically stable at room conditions, like how Form 5 is most stable for chocolate. But diamond persists indefinitely because the energy barrier to transform into graphite is enormous. Similarly, Form 5 chocolate is kinetically trapped in a stable state. Both systems illustrate the difference between kinetic and thermodynamic control. The system gets trapped in a local energy minimum that's stable enough for practical purposes. How is chocolate tempered industrially? Small batches can be hand-tempered using the three-stage process, but large-scale production uses continuous tempering machines. Continuous tempering machines have 3 temperature zones corresponding to our 3 stages. Chocolate flows through heating, cooling, and reheating sections in sequence. Another method is seeding. Pre-crystallized Form 5 cocoa butter, called seed butter, is added to melted chocolate at 31 to 32 degrees. The existing Form 5 crystals act as templates, propagating throughout the batch. Typically, 1 to 2% seed butter by mass is sufficient. The seed crystals multiply exponentially as the chocolate cools. The crystal propagation rate is faster with more seeds because you have more growth sites. But too much seed can cause the chocolate to thicken prematurely, making it difficult to work with. Let's summarize the chocolate tempering paradox. Why does careful heating and cooling matter? First, cocoa butter has 6 distinct crystal forms, each with different melting points and stabilities. Second, Form 5 is the desired form because it melts at 34 degrees, giving room temperature stability and pleasant mouthfeel, but is kinetically difficult to nucleate. Third, the 3-stage tempering process manipulates temperature to preferentially nucleate Form 5 while suppressing other forms. Stage 1 erases all crystal memory by fully melting everything above 45 degrees. Stage 2 creates Form 5 seeds by cooling to the critical nucleation window of 27 to 28 degrees. Stage 3 eliminates competing forms by reheating to 31 to 32 degrees, leaving only Form 5 to propagate. The final result is stable, glossy chocolate that snaps cleanly, resists bloom, and melts perfectly at body temperature. Let me pose a thought experiment. What would happen if you tried to temper chocolate at 35 degrees Celsius instead of the standard protocol? At 35 degrees, Form 5 melts, so any Form 5 seeds would immediately dissolve. The chocolate would remain liquid. What about 33 degrees? This is just below Form 5's melting point. Form 5 could theoretically nucleate, but the driving force is very small. Nucleation would be extremely slow, taking hours or days instead of minutes. What about cooling directly to 20 degrees? This would create huge supercooling for all crystal forms. You'd get rapid nucleation of forms 1, 2, and 3 simultaneously. The chocolate would solidify quickly but in the wrong forms, giving poor texture and bloom susceptibility. This shows why the 27 to 28 degree window is so critical. Too hot and Form 5 won't nucleate. Too cold and the wrong forms dominate. The process requires precision within about 1 to 2 degrees. The chocolate tempering paradox has implications far beyond confectionery. Polymorphism and crystal control matter in many fields. In pharmaceuticals, different crystal forms of drugs have different dissolution rates and bioavailability. Controlling which polymorph forms during manufacturing is critical for drug efficacy. In metallurgy, heat treatment controls which crystal phases form in steel and other alloys. This determines hardness, ductility, and strength. In food science, margarine, shortening, and other fat-based products use similar tempering principles to control texture and melting behavior. The underlying physics is universal: nucleation barriers, kinetic versus thermodynamic control, and the manipulation of thermal history to achieve desired material properties. Here's a final question. Can you skip tempering if you're going to eat the chocolate immediately? Technically, yes. If chocolate is consumed within minutes of solidification, the crystal form doesn't matter much. It will still melt in your mouth. However, the texture will be wrong. Untempered chocolate is softer, more prone to fingerprints, and has a waxy mouthfeel rather than a clean snap. More importantly, it won't store well. Within hours to days, bloom will develop and the chocolate will become crumbly. This is why professional chocolatiers never skip tempering, even for products consumed quickly. The quality difference is immediately noticeable to trained Pilates. The chocolate tempering paradox beautifully illustrates how materials, science, thermodynamics, and kinetics combine to create everyday phenomena. A single melting point number doesn't tell the full story. The path taken to reach that state determines the material's structure and properties. Careful control of thermal history, down to degree-level precision, is essential for achieving desired outcomes. The paradox is resolved when we understand that cocoa butter's 6 crystal forms have different stabilities, and the tempering process selects for the optimal form. Next time you enjoy high-quality chocolate, remember, you're experiencing sophisticated materials science, optimized over centuries of trial and error, now understood through thermodynamics and crystallography.